In this video, we will discuss how to define the oxidation state of the melt, which will be used during the calculations. The oxidation state conditions which will be used are set in this portion of the petrolic main form. At the top, the blue label shows what conditions are set now, and at the moment the calculations will be performed following an oxygen buffer and specifically quartz phyllite magnetite QFM buffer of oxygen fugacity. If we want to change this, we click on this label, and in the form melt oxidation state that appears, we can choose one of the four available options for setting melt oxidation state, and that's effectively how the proportions between ferric and ferrous iron will be determined. The current option which is used is oxygen fugacities, and that's an option which is used very commonly during calculations, and it's specifically useful if one tries to reproduce the results of experimental work, because when experiments are conducted, oxygen fugacity in most cases is controlled using oxygen buffers. If you want to change oxygen buffers, you click on this blue label which says currently QFM, and you can see the available buffers which can be used. This plot on the right shows their relative position, so which ones have higher oxidation state, and that's higher oxygen fugacity, and which ones have lower. It is also possible to set a constant offset to the oxygen buffer which is used, and offset is set in the log units. And let's say if we say number 1, what this effectively means that we will use QFM, and QFM is this buffer here, but the oxidation state will be higher by 1 log unit, so it will be a parallel line going slightly above the QFM. If you set it negative, -1, that will be following the buffer which is below the oxygen fugacity, which is corresponding to the QFM buffer. You can obviously change which buffer we use, so at the moment if we click OK, then the calculations will be performed using a Wüstite magnetite buffer, and you can see that Wüstite magnetite buffer is this one, and we will be even more reduced by 1 log unit than the Wüstite magnetite buffer. So that's how one can set the oxygen buffer depending on where you want to be, and by using this shift value you can actually cover a very wide range of oxygen fugacity if that's required. Another common option for setting the oxidation state of the melt is to use a system which is closed for oxygen. This is the most common option which should be used when modeling crystallization in natural magmas, as in most cases during crystallization of natural magmas there aren't any natural agents that can buffer oxygen fugacity, so the oxygen fugacity is determined by the composition. So if we want to choose this option, we just choose closed system for oxygen, and if we now click OK, you can see that the chosen option is now closed system for oxygen. One important consideration when using this option is that you need to provide the initial iron 3+ and iron 2+ concentration, so the ferric and ferrous iron contents in the melt. And if, as in this current example, we have 0 for iron 2O3 and we choose this option, all that means that all iron will be considered as iron 2+, so there is no ferric iron during crystallization. So obviously if we want to use this option, it is important to know what proportions of ferric and ferrous iron you would like to have in the starting composition. And let's say if we choose 1 and 8, so that will be around 12% or something of the ferric iron in the system, we can use this option, and in that case we will be told in the output what oxygen fugacity this corresponds to. If we just do a quick calculation, you can see that extent of fractionation is set now to 0. So if we just have a look what it tells us, so with these proportions of ferric and ferrous iron, the oxygen fugacity at the liquidus temperature, which is determined by this model of Ford et al. Wolvin, is around 1848, and it's QFM minus 0.07 log units. Another option which is available in Petrolog is to set the reference buffer, which will be telling you what is the offset to that buffer of the current oxygen fugacity. To do this, we need to go into Tools and Options, and you can see in here this is the reference buffer. So that's not the buffer which will be used to set the oxygen fugacity. It will be a buffer which will be used as a reference to tell you how far off that buffer you currently are. So, for example, if we use wüstite magnetite and repeat the calculations as we done before, so with the first run, when the reference buffer was QFM, we got an answer that our oxygen fugacity is 0.7 log units below QFM. If we run it again, you can see that it's now very close to wüstite magnetite. It's 0.1 log buffer above, log unit above the wüstite magnetite buffer, this particular oxygen fugacity at this particular temperature. If we change the proportions between iron 3 and iron 2 in our starting composition, this will obviously result in different calculated FO2 and also the different value of the offset from the reference. There are other two options. One is constant iron to iron 3 ratio. These are already specialized options which shouldn't be really used very often. This is useful when trying to understand the relationship between the ratio of ferric to ferrous iron and the oxidation oxygen fugacity. That's how you can do those specialized calculations. And the last one is a function of olivine composition. So it's obviously only applicable if olivine is crystallizing from the magma, and you also need to know how to set those values for A and B. And my recommendation would be, if you want to use this option, just email us, explain what you're trying to do, and we can suggest how to use it. But as I said, these are specialized cases, and in most situations you would either use an oxygen buffer or a system closed for oxygen. Now, before we finish, there is one more consideration which needs to be done, is which model we use that sets the melt oxidation state. And you can either go this from this form, or you can click on change oxidation models, and you can see that currently the model for iron is Borisov et al. 2018. Overall there are 6 different models, and certain things during calculation will change if you choose a different model. We've put a presentation on the website on the implications of choosing different models and what would be the particular settings that are important to consider when thinking of choosing the model. And please, if you're interested in this, please look at that presentation, and again, you can always send us an email with the question. This presentation doesn't discuss how to set the sulfur oxidation state. That will be a different tutorial.